Resuming our conversation, we are now back on the master stage for the first panel of the day here on the master stage. And the change of topic, we will now address quantum resilience with a panel entitled Quantum Resilience for Space Systems, Preparing the Transition to Post-Quantum Security. And I will leave the floor because the moderator of this panel is Erin Miller, Executive Director at Space ISAC, our sponsor. Please help me welcoming Mrs. Miller on stage. With 4 panelists, I'm handing over the microphone and my role starts and stops there.
Thank you. Yeah, I'm sure after a coffee break, quantum is probably not what you wanted to talk about, Margot.
Well,
but it is what we want to talk about. Come on over, have a seat.
Make yourself comfortable.
Yeah. Should I scoot over one? Okay.
And a wonderful session.
All right. Well, thank you, everyone. We're here to talk about quantum resilience. And what we're going to do is we're going to remove all the hype from the topic of quantum so that you can do this topic after lunch and after a coffee break, shortly before happy hour. So I have an esteemed panel here with me today, and I'm going to allow them to talk more about themselves in a second. First, I want to set the stage by letting you know that Space ISAC, where I work, we set up a quantum community of interest about a year ago. It's taken us like a year to figure out how to remove the hype from the topic of quantum, because there's just so many terms being thrown around and so much concern about if quantum computers will break everything or if QKD will save us all. So I've got a panel of experts here that are going to walk us through some of these challenging topics. Space systems engineers have to navigate real trade-offs. They have to deal with the true challenges that program managers do of cost, schedule, and performance. So they have to make real decisions related to space systems that are complicated, with legacy architectures and space hardware that sometimes takes decades to design and get through the entire life cycle to deployment and operations. So our real question here that we're going to start this panel off with is, what is going to be the most realistic and deployable, sustainable solution for quantum? And what the heck even is the difference between post-quantum encryption and QKD? They're not the same thing. It's like a bad joke, like they are both going on a date and they finally break up, because they don't really belong together. They're not the same thing at all. Right, Antonios?
They are not at all. The only common thing that they have is that the fact that they have this common quantum word. Otherwise, they're completely different. Should we explain a bit what is the difference between the two?
Go for it. And introduce yourself, too, if you don't mind.
My name is Antonios Atlasis. I'm the head of the System Security Section at Tech Directorate. It is the Directorate of Technology, Engineering and Quality, and our job is, among others, of course, to promote security in space missions, including the cryptography, post-quantum cryptography, and how this will evolve in the years to come.
So that's your job. So that means you can tell us the difference between the two.
I believe so, yes.
Can you elaborate a little bit?
Sure. So first, let's start a bit of to understand what is the quantum threat to cryptography. For years, we have been using cryptography, which is based on mathematics, which is based on formulas, which is based on solving complex problems, and the complexity of solving these problems is making sure that the systems will not break. Now, there are different types of cryptography. This is so-called symmetric and asymmetric, and it is important to understand this differentiation. Why is that? Because when the quantum computers will materialize, at least at a state that will be good enough in order to make many hard computations, they will break cryptography. They will break the conventional cryptography that we use nowadays in every single aspect of our life, of our everyday life, in our smartphones, in our computers, on our smart cards, on everything. The thing is that this quantum computers, they will use some algorithms behind, and these algorithms have different effect on symmetric and to the asymmetric part. So they are believed that they will break the asymmetric ones, but the good news is that the symmetric ones will not be affected, at least not that much. There is also a debate here how much it will be affected. In the worst case, I would say that we will just need to double the size of the keys, of the symmetric keys. In the best case, we may even need to do anything. So the good news is that the symmetric crypto is not affected by the quantum threat, while the asymmetric crypto we use nowadays is certainly going to be affected. All this is the typical cryptography used nowadays. The asymmetric crypto, which is going to be quantum resistant, meaning that it will be based on different mathematical problems that will not be solved or solvable in a reasonable time by quantum computers, is called post-quantum cryptography. This post-quantum cryptography has nothing to do with quantum systems or QKD systems. On the contrary, QKD systems are based purely on maybe not purely, but certainly one part of them is based on quantum technology. And this is where the differentiation between the two lies.
Thank you. So what I'm gathering is that post-quantum cryptography is like at the surface level, like the application level, and then quantum, like real quantum, is more like designed into the architecture. Would you agree?
I would say that post-quantum cryptography can also be at the lower levels, can also be used at data link layer as well, and nothing forbids to do so. The fact is that post-quantum cryptography, or in general, allow me to say that traditional cryptography as we know it, the one that is based on maths, can be used up to the application layer, which of course brings many advantages. It allows, for instance, the end-to-end protection from the application messages we have, for instance, in our smartphones. It can still be used on the lower layers. The fact is that if it is used on lower layers, it brings less benefits, that's all, but it can be used at lower layers as well.
Thank you. So, Cyrille, I want to give you a chance to introduce yourself here and also ask you, since you're working at the frontier of quantum communications, do you see quantum key distribution as a realistic path for operational satellite systems, or will post-PQC remain the dominant approach for the next decade?
Thank you, Erin. So, Cyrille Laborde, I'm in charge of quantum communication and optical communication development in Thales Alenia Space Telecom. So my main work is to, let's say, move to R&D on the labs to commercial applications, what is not the easiest path to proceed. Coming to your question, so what's regarding PQC and QKD is always the question: what is the best case? How we can compare them? I think that cryptography today is like energy. In fact, that you don't consider we can compare to nuclear power or solar power. In fact, we need both. And I think for crypto, it's becoming a critical resource. And we need PQC and QKD, and we are dealing with both systems in our development. For instance, to secure the ground to satellite links, we don't clearly imagine to use QKD to secure these links, because this would need to have a quantum receiver, physical quantum receiver on board satellite, so meaning a telescope plus a cooled system to receive photons, and this becomes very difficult to install on satellite. So we think PQC will still secure the links between the ground and the satellite, and it's important to move forward in this technology. However, satellites are more becoming, let's say, a service provider of cryptography. We are designing some satellites in order to provide keys from space, but it's to secure communication on ground. So we deliver keys to the users on ground through the satellite, and these keys are able to be used for classical communications. And for that, we have several. We are dealing with several developments. First is what we call prepare and measure, so the BB84 protocols, and this is developed today by ESA through Saga in Italy, in Thales space. We are developing also GeoQKD, so QKDs that are able to be delivered from geostationary satellites, so to see all the users at the same time. So we are moving in this direction of QKD as well, by not knowing at the end of what will be the real operational. We don't know yet what the business case is not yet established. Now, it's to be very clear, we are building it, but it's not yet established, and we are moving forward also. Again, to prepare the entangle-based security based on entangle-based protocols, so BBM 92. And why we are focusing now on that? Because cryptography is not the only objectives of the quantum technologies. We are dealing with quantum communications now, and the objective will be further to connect quantum computers, quantum sensors, and and cryptography will be one use case of these satellites that will deliver resources. It's a new resources, it's a new market to address, to deliver quantum resources on ground for cryptography first, but then for connecting and to make the quantum internet afterwards. So there's no competition, let's say, between PQC with algorithm and mathematics on one side and QKD on the other side. It's just we have to master both technologies to be able to use to have them in our portfolio and to secure as much as possible the systems.
Well said. Did you all get that? There is going to be a test at the end of this. I'm going to press you more on that operational piece later and the business case. We're not quite there yet. So, Johanna, I want to ask you to build on this a little bit here. So for spacecraft that are already in design or production, what are the most practical steps industry can take today to introduce crypto agility without fundamentally redesigning the mission? And if you don't mind giving us a little bit about your background too, that would be awesome.
With pleasure. Good afternoon. It is a pleasure to be here. My name is Johanna Sepulveda. I'm the senior expert on quantum secure communication for AIRBUS Defense and Space. I'm also the technical domain manager for quantum technologies. So that means that in my daily life, I deal with the road mapping of the quantum technologies for AIRBUS Defense and Space, but I also work as a technical authority and also engineer in different projects in the area of quantum communication, quantum sensing, quantum computing, and post-quantum crypto. So I love the topic. So I'm very happy to be here. So regarding what is happening now, so we hear now that we have this threat, that it is threatening the cryptography, the symmetric, and the public key cryptography. Symmetric cryptography can be patched, so I think we have a solution. Currently, many of the crypto and encryption mechanisms that are using in space is based on symmetric cryptography. And we are already using AES 256, so that means that we can be already quantum secure. However, what happens when you use symmetric cryptography, so that means that you already have to preload the keys. And this has some limitation, mostly if we are talking in the part of big constellations. And now we see which is the role that space is having in the defense segment. So that means that now we are going to have to work in coalitions where we have to engage different nations, nations that have adopted different rules of engagement that can be changed at every time. So that means that we need scalability, we need adaptability, and for that we need asymmetric public key cryptography. So public key cryptography. What is the role of the public key cryptography? Basically two. First, to do the key exchange, and the second is to provide authentication, so to ensure that you really are talking with the party or the component that you have to do. For that, you need a post-quantum crypto. Then we have several challenges, because the post-quantum cryptography you also can use quantum communication for exchanging this case. But let's talk about the post-quantum cryptography. Huh? In the post-quantum cryptography, there were already since 2016, they start a competition about these cryptographic algorithms. Already finally in 2024, 2025, we have the final standards of post-quantum crypto. So are we ready there? No, because to have the standard is not enough. It is required to know how to integrate into an efficient way into the space. Currently, we don't have a public key infrastructure into the space, and that must be defined. We cannot adopt TLS because TLS has a lot of drawbacks. And more for the traffic of the space. So AIRBUS, what we are doing already is dealing with crypto agility. So that means the possibility to have new cryptographic methods, and that it includes not only crypto agility for post-quantum crypto, but also for QKD. You have to plan ahead, not only the hardware, but the software that have to be embedded into the satellite in order to enable the upgradability capability of the satellite. We are also doing other approaches in the sense that in order to adopt crypto agility, you don't only think to have to think in modularity. You have to think on interfaces, attestation, and secure supply chains. One also path that we're having is the securitization of the ground segment. And in the ground segment, we believe that by using not only the standards, but also what is going by the IETF, all the standards for internet, we can use it in order to secure the ground segment. We have to think on hybrid architectures because currently the recommendation is use a cushion approach. So that means that you have the traditional crypto, on top you put post-quantum crypto, and for some critical applications like governmental, securitization, critical infrastructure, defense use cases, you use QKD. So this is important that these all cushions work together in order that even if one of these cushions or one of these layers is broken, we are not going to get without security. And I think the last part that we are also working on, it is engaging with the community in order to work with the standards. So a standard is very relevant.
You have convinced me that we should have both QKD and PQC. And I hope our audience is gaining some opinions on this as well. I'm looking for your questions before we get to the end of this session, so be thinking. So in order to do what you described, all of you, then we're really going to need some encouragement of industry. So I know from my own experience working technology transfer like you do, Sabrina, that part of the job of a university is actually to work towards an understanding of and research towards policy, regulation, understanding how to encourage industry to adopt new technologies like this. Do you have any examples or experiences that you could share that would inform this perspective?
Yeah, sure. Well, firstly, thank you for the invitation to be here. And the panel, as you can tell, very informed and very esteemed. So happy to have this discussion. I think, the point of what I want to say is a bit from a different lens. And by that, I mean, my background, I've worked in the space industry, on the technology side, in the industry side, consulting, and now I'm with the University of Luxembourg within our SNT center. And I work in technology transfer, and so it's really, I would say, in the layer between all of the research and basically all of the background that goes, and the R&D that goes into kind of what was discussed. But actually, well, what does it mean for industry and governments, and how can you implement that? So how do you take it from idea, innovation, to, well, what does this mean? And one of the things that we find, especially within research, is that the technology is not necessarily a challenge, but what is a challenge is actually what was said earlier. I mean, how do you deploy this in a way that infrastructure can keep up? How do you deploy this in a way that industry understand? How do you standardize or on different layers of this? And what we mean by that is, okay, well, we've got great ideas. we've got great engineers, we've got great scientists that are coming together and researching on these different topics, but actually we're collaborating with industry to say, well, what does work for you? How do we adapt your infrastructure, not from a satellite perspective only, but actually from the ground infrastructure? How do we actually take the different layers? How do we look at our value chain and supply chain and say, well, where are what needs to be adapted to make this operational? And I think this is one of the biggest challenges we have. And then you have not just space, but other industries that are trying to keep up with regulation and policy, looking to adopt, such technologies. And honestly, we're finding that there is a big blocker. And people, as you said, aren't necessarily aware of the difference between, the quantum key distribution and PQC as well. And so what we're trying to do in the Tech Transfer Office is try and bring that to light and actually have those conversations with everyone in the room on a very kind of basic level, and actually just talk more on a practical lens of, well, what is needed, where are the blockers, where are the challenges, and not so much on the pure tech side, if that makes sense.
Definitely. Sounds like you are absolutely serving in the right role as the Tech Transfer Office. So we have now an opportunity to answer one of the hardest questions, which is about assumptions. For all of you, but back down to you, Antonio, starting with you, what is one assumption the space sector is getting wrong about the quantum threat? What do you think the quantum threat is? And what's the consequence if we don't correct it in time?
Thank you. Allow me to go a bit back, because there were many, I would say, things said in this round. Of course, it's connected with your question. Very correctly, Johanna mentioned that in space you use symmetric-based crypto for one reason or another, mainly because of the simplicity and on the less overhead on performance, etc. So, based on what we discussed before, the good news is that our systems, space systems, are not affected by the quantum threat because they rely currently on the symmetric crypto. Having said that, I don't disagree with you that while for the time being we are good, we should also foresee the future, and for the reasons you mentioned, like scalability, etc., but also for some other reasons, we need to go to public key cryptography also in space, for instance, to have some additional security features like forward secrecy and post-compromise security. And maybe if you ask me regarding the assumptions, maybe one of the assumptions kind of not necessarily so far heavily considered for every single mission is the need of this post-compromise security and forward secrecy, which again can only be provided by the asymmetric crypto. But as far as the quantum threat to crypto is concerned, I'm happy to say that based on what we discussed, the space systems are not affected. We just need to plan for the future. We have already planned for the future. We just need to move fast, to move even faster than what we are doing today. Allow me to say here a few things about what we have done so far, because there were a few mentions about, for instance, TLS, about PKI, etc. Yes, the standards on the post-quantum crypto are relatively new. The first one was standardized, if I'm not mistaken, a couple of years ago, MLChem. Of course, we knew more or less what was coming through this competition that started, as mentioned, since 2016. But in space ecosystem, we have been working on this, I would say, at least since 21. We work together with the research community because, of course, we acknowledge their value. And I'm happy to say here, to share that in Europe, we have great cryptographers. And many of them are behind some of the solutions which have been standardized or are going to be standardized by NIST. So we must be proud about it. So as a European Space Agency, what we did is that we worked with some of these very famous cryptographers, and they built a protocol for us, for space systems. And this protocol is currently under standardization in CCSDS. CCSDS is a standardization body for space systems. It's like the ITF that you mentioned, but purely focusing on space system. It has nothing to do with TLS, etc. It's mainly on layer 2, because up to now we use data link layer protection space systems because usually we have one-to-one or no too many, but without any kind of intermediate nodes, at least not yet. So all in all, if I would to conclude with this, I would say the currently used space systems are not affected, as mentioned, by the quantum threat to crypto. This is a good news. I do agree that we need to move to the post-quantum. If it is about the assumptions, I would say that let's move to solutions that offer some other attributes as well, like forward secrecy and post-compromise security. Allow me only to disagree in one thing with some of the panelists here about that we will need both. I would not rush for any conclusion, don't get me wrong. I'm not against on promoting technology development of quantum. I find it extremely important, honestly, for many reasons, because the quantum technology will pave the way for new opportunities in general. But I would not draw any conclusion yet, at least for the usage of the quantum on QKD on the crypto part. We can discuss it later, of course.
I just wanted to maybe add one point about having both. And I think in the short, we're talking about different horizons. So the short, mid, long term. Long term, completely agree that we should kind of make up our minds. Do we, which one do we want to go for? However, actually in the short term, the problem is in order for us to go down the QKD approach, there's a lot that does need to change from an infrastructure perspective. And I think that approach might be a bit too shocking and quite a heavy investment in the short term. So actually, when we're talking about this hybrid model, it's really, I think, Johanna, we had a conversation before, you mentioned this kind of cushion effect of actually, let's do it, in a way that we can adapt with the time, in a way that everyone can keep up, can keep learning, and then eventually get to kind of a final model. But actually, I just want to mention as well, from a policy perspective, Europe has been pushing a lot on, this kind of post-quantum security lens and actually incorporated a directive to enforce this. But actually, what they're doing is more on the PQC side rather than the quantum key distribution side. So we're kind of getting mixed messages at this point about, well, which approach do we take? Which is why we're seeing this hybrid model continuously being talked about in the short term.
If I may, first of all, maybe need to clarify what you mean about hybrid model, because it was mentioned by Johanna. I believe I understood you refer to the combination of pre- and post-quantum cryptography. This was my understanding, or not?
So when I was talking hybrid, so there are different kinds of hybridization. The classical post-quantum, but also the classical post-quantum and quantum that we have for certain applications that have higher levels of security, the three cushions. Currently, for example, in USA, the NSA, it is recommending to use post-quantum without any cushion. Do only post-quantum. Here in Europe, the national security agencies of Europe, they are advising to use the cushion approach. And I think when we have a cushion approach together with the quantum, it might open even in a more smooth way the adoption of quantum as well.
May I take it?
Go for it. And then I really want to hear from Cyrille.
Yeah, sure. I finish with this. Okay. Again, I agree on what you said about the hybridization that it did in the US. They say you don't need it. You need to use only post-quantum. You are good. And that the European ones really suggest to use a hybrid approach, where hybrid, they mean combine post and pre-quantum. They do not mean use post-quantum with QKD. Just to be very clear on this. And secondly, because it was mentioned about long-term and short-term, especially if we think about the short-term, and the short-term, the transition has to happen until when? 2030 for critical infrastructure. So in principle, it means tomorrow. I really doubt that the QKD technology will be mature enough until 2030, maybe even 2035 or whatever. While on the other hand, I can say that on the post-quantum crypto, okay, the algorithms are there, the developments are ongoing, not only on the IT terrestrial world, but also in space. So I find it much more reasonable and I would say similar to move to post-quantum technology by these critical days.
See, maybe I want to come back on the space criticality, the space threats, and I agree that for traditional systems, by using symmetric keys, we are not really affected by post-quantum, and I agree with that. And most of applications are not in danger now, but the criticalities will be for sure for next constellations, because we have two markets now. Finally, we have the classical one, but we can secure as it is now, and we are quite in a good position. But for the next, we will rely on finally what is going through is that we are relying on ground technologies. Finally, we are putting in space ground technology. So as the space systems will certainly follow what is on ground. So the criticalities that are on ground will be also on space, and this will follow this approach also in space, and by also considering that the constellations are quite short lifetime, so they can follow. The only problem is that you need to invest, upgrade your system, and to follow what is going on ground. So, as not saying that there's no significant difference between the threats we will have on ground or the threats we will have in space for development of this constellation.
Oh, go ahead.
May I comment? Because in this question, I think we were talking about what we are missing, and we already enumerated the different challenges regarding the impact, sensitivity, migration kind of challenges. But I think what we are missing is the opportunity. So here also we have a very nice opportunity, even for the space segment. Currently, there is a challenge when you have you need to make secure or ultra-secure communication among different domains, for example, among different countries. Currently, it demands that the countries have bilateral agreements so that the secure connectivity can be taken or can be carried on by these two countries. Currently, in space, we have a regulation in Europe, for example, that creates the background, the baseline for this to facilitate this multi-country connectivity, and that is the Secure Connectivity Program that was created as a baseline framework for the IRIS Square, and that it is a unique opportunity for space for enable this multinational connectivity backbone that enables these, for example, coalition efforts in an easy and secure way.
Thank you. So we have had some good discussion here about the operational capability and the maturity of these capabilities. I want to dig a little bit deeper on that topic to get to what is really realistic and deployable. So we haven't hit on quantum sensing yet. Maybe just for the benefit of our audience, you can maybe we can just go down the road and we can kind of rate the maturity of the technology between PQC, the different types of QKD, prepare and measure, and the entangled types, and quantum sensing, and maybe give a few examples from your perspective of how mature these capabilities are and ready for deployment.
The quantum experts? I can talk about the maturity of the post-quantum, but for the quantum technology, I leave this to you.
No, I can talk about the maturity of QKD. QKD, yes. So we are. I think technology now are quite mature. As this QKD is working on ground through fiber optics. We are now all the space equipments. Photon source, single photon source, synchronization units are now already at more than a breadboard level, so because we can underline that, for instance, some demonstrators are already flying. Eagle 1 is going to fly by the end of the year, so we see that the technology, the QKD technology to be embarked on satellite is mature enough. What is not mature yet is the certification. That to ensure that the keys made by this system are, let's say, certified and you can use it certified by national security agencies, and you can use it for governmental communications, etc. Maybe it's possible for private companies can rely on what is presented by the operators, but for governmental communications, QKD is not yet ready. It's ongoing, and I think that the objectives of this is one objective of SAGA to enter in this certification process, and the way to do SAGA is already in the frame of a cybersecurity process. So it is the case for entangle-based QKD that is much more secure, as we have no keys on board satellite, so it's a much more secured system because you don't have to you don't have the famous trusted node on board satellite, so you deliver 2 photons at the same time, so entangled photons, so it's a much more secure systems. However, we are still in first demonstration phase to demonstrate that we are able to master the entangled photons received on ground and to do something with them. So we are more in, let's say, in 10 years, between 5 to 10 years to achieve these demonstrations. And again, this is our roadmap. And if we are able to proceed with these technologies, it will be completely, it will change many things. And again, not only cryptography, but also quantum communications, because it will be the way to proceed to connect quantum computers, quantum sensors, and to move forward. But we are a bit longer time than QKD. But it's important that I always insist, because sometimes we heard, oh no, it's not necessary to invest on QKD because we are not sure it's necessary with respect to PQC. But however, if we don't move on QKD, we are not moving on technologies that are quite similar for quantum internet, and we are not ready to prepare the quantum internet behind. So it is important to understand it's not only focusing on cryptography, but it's larger, wider range of applications that we are preparing.
Thank you. Go ahead.
Okay, thank you. Here I might make a small advertisement, just heads up. So I think, as it was said, for example, in Europe, they have a huge investment since 2021 in order to deploy what is called the EuroQCI, European Quantum Communication Infrastructure, to be deployed in the terrestrial and space segment. These foster the development of the different building blocks in the terrestrial part, but also in the space part. In the space part, there were some elements that also you can take advantage and leverage on them. Like, for example, in order to have a very good performance, you need a large aperture satellite optical terminals, and that is something that, for example, AIRBUS has decades of heritage based on the programs on the Earth observation and also the different programs of optical communication. So all these heritage can now be transformed in order to support and enhance the performance of the QKD. So there are some elements that are already mature and can also be integrated in this part. We are also the providers of the optical ground station for Eagle 1. So again, we take advantage of our heritage on adapted optics, PATs, in order to adapt to this and working with the community. Now, regarding quantum sensing, so quantum sensing is one of the most mature quantum technologies when we compare to the different pillars. That means quantum computing, communication sensing, quantum sensing, they are very advanced. So, for example, in the International Space Station that will be deprecated in the next years, they already quantum clocks on it. Now, Star Lab, that is also AIRBUS is part of this consortium, will be the next generation International Space Station, in which already Voyager will integrate optical clocks. There are also other companies that will integrate in experimental matter some gravimeters. There is also a Pathfinder flagship project here in Europe in order to develop these gravimeters in order to enhance Earth observation, and we are part of it as well. So there is a huge focus on the integration of these quantum sensors in space for enhancing not only Earth observation, timing, position, and navigation capabilities, but also for many aspects of defense, like surveillance, ISR, etc. So that is a huge push. They are already in integration. Some of them are already in orbit. And so I think now what is also being discussed is the economy based on these quantum sensors or quantum technologies in space.
Thank you. Antonios, did you want to add anything about maturity of PQC?
Yes, sure. So I believe PQC is a bit ahead, to be honest with you. I will give an example. If you use, for instance, Google Chrome, it is already using post-quantum cryptography, at least when you connect with the Google service, certainly you employ post-quantum cryptography, even if you don't realize it, it's completely transparent to you. Also, major, I would say, providers, maybe I should not name it, but I will do in order to make it more tangible what I'm saying, for instance, like Cloudflare, they already have implemented and using post-quantum crypto, protecting their traffic using this technology. So I believe it is way ahead, to be honest with you. Indeed, there are some demonstrations of QKD technology. We need to understand that these are demonstrations, and I fully agree with what was said, that indeed a big problem now seems to be the certification as well, how to achieve this part on QKD. And of course, I also agree with what you said, that still we need to invest on the quantum technologies, because at the end of the day, it's not only about QKD, it's about the quantum technologies in general. And I really believe as well that we need to continue investing and promoting this technology. But on the other hand, if I need to compare the maturity level, I believe post-quantum is much more mature, and it's not a coincidence that all the major security agencies from the US side, the European ones, from ANSI, BSI, the Dutch, the Swedish, Italian, etc., they have signed actually a report, a paper together saying that they believe the solution to the quantum threat to crypto now is the migration to post-quantum crypto. I believe this says everything.
Thank you very much. I appreciate all of your responses, because I learned something, which has got to be a good sign, because that means that there's people here who are learning something too, because I know we don't know everything about quantum. There's no way for everyone to know everything about quantum. So Sabrina, from what you've heard about the maturity of these technologies, how do you think the university could help and contribute to further advancement and commercialization?
Yeah, sure. Well, actually, I completely agree with the comment about PQC being much further ahead and actually being, I would say, pushed on a bit more, especially in Europe. I mean, what we're seeing now at the university and the collaborations we do with industry and kind of where the funding is coming from is less so right now on the quantum side. And it's interesting kind of what you've said by that, because there have been tangible use cases where actually you can do it, the technology is available, but it needs to be more mature, but research has been done in that area. But actually what we're seeing that industry in Europe and so on actually want is more advancement on the PQC side, which is why we say definitely from an investment perspective, a resource, a time perspective, I do see maturity in there. But then you have the larger players who actually have the means to invest, the means to explore, be innovative, more focused on the quantum side. So I think we're just seeing kind of a mixture right now, and it's also about capabilities of industry players that actually want to use such technology, and then you have European or governments rather that are kind of coming in and pushing their certain technology or research priorities on the university as well. So we kind of have an influx. I mean, University of Luxembourg is working in all of these areas, but yeah, like I said, we're seeing kind of more push and pull rather from the PQC side. In terms of where the university plays a role, I think one of the key challenges is addressing those gaps and actually taking the opportunity of, well, how do you deploy this now? And that's where we as a university research that and take it from the tech and the idea to actually, well, how do we now at each layer look at, well, what is needed? We don't have to spend tons and tons of money. We replicate this in our labs. We do kind of the groundwork on this before we then go to industry and say, now test it in real life. Go and try this out. And that model, I mean, allows Europe and allows industry to actually adopt. And so hopefully in the next 5 years, we'll see a significant shift and greater maturity in these two different areas because of the work we do at our university and I'm sure academia in general.
Thank you. Yeah, universities and government most certainly influence the timeline in which industry adopts technology. So we have a question from the audience of, in how much time will QKD be certified by agencies? Does anyone want to take that question?
First of all, just to clarify something, ESA is not a certification agency. It's not ESA to certify. Whatever certification is provided for security purposes is done with the support of the labs, but by the national security agencies, the corresponding national authorities. Now, honestly, it is hard to say. It's very difficult to give this answer because, yes, there has been efforts for quite some years now in order to standardize the process that to be followed in order to certify the systems, and some of these efforts are led by some of these national security agencies. For instance, under HA, I believe that there was a lot of work from BSI, for instance, but in order to give you a timeline, I believe that I cannot do it. Yeah, it's a bit difficult to assess it.
Thank you for your honesty, especially about ESA not being a certifying agency. When it comes to handling classified information, how will a federated layer be managed to communicate different national domains? How can an EU PKI help in this effort? Anyone want to try that one?
I can take it, but I don't want to monopolize it. So if someone wants to answer, by all means.
So I think also that refers to what I was talking about, the opportunity of a space, and based on this secure connectivity baseline regulation, in which enables a common understanding of what the level of security means. Because when you talk and when you connect interterrestrial, even for example, if we talk about EU secret level, each country is sovereign of implement and decide how they are going to implement this. So that means that we have heterogeneity in the nations, even when we have a single security level. That is why it is required bilateral kind of agreements, so that each party or each country can look at and the implementation, can certify or can test that it is and approve that it's secure regarding some criteria, stamp at one side, stamp at the other side of the border, and then they are considered secure. But if you have a common regulation in a space and it is considered an international domain when everybody has the clear rules, then we can communicate cross-border and in this kind of multi-federated system through a space. So it is a way.
I just want to jump on that and then I'll hand it over more from a regulatory and then directive point of view. So the Euro QCI, feel free to check it out. But it's actually putting together, I think to Johanna's point, all the 27 member states within Europe. And sorry, I know I'm talking very much from a European lens here. And they're actually saying, now we need to work together to find a standardized solution where we're all happy with this. And honestly, that is needed because take a look at, I mean, Eagle One was mentioned. You know, we're looking at future systems, Iris Squared, for example. And so actually European collaboration, European sovereignty, this is exactly where we talk about that. And where we talk about this resiliency layer on a European level. So Europe is making waves to actually collaborate further with each of the member states. So things are being done on that level and things are being pushed from that European perspective.
Mm-hmm. Well, last year I had the fortunate opportunity to be on a panel where we talked about the definition of sovereignty. And it was because it was like a new word last year for some reason. It was like the word just came out of the dictionary or something, and we started talking about it. But what we learned, one thing I learned from that panel, is that when we feel comfortable with our sovereignty, we collaborate more. So I think that this makes a lot of sense that we would adopt more technologies, and that would be part of the incentive. I have another question from the audience, and it is, all PQC algorithms are quite new. So with a NIST finalist being broken late in the selection process, do you have confidence in current standardized PQC algorithm, or do we need crypto flexibility to change algorithms in case of future compromise?
Okay. First of all, it is a very valid point. Maybe to say one thing, that the technology, or part of it, because the post-quantum solutions are based on different mathematical problems. There is not one family, there are different ones. Some of them are not really new. Some of them come already since 1979, and they're considered to be very mature. But it is true that some of the finalists, these finalists, were broken just in the very end of the competition. So this can go wrong. This can happen. This can happen with any algorithms in principle, even for standards that we use for 25 years now, like IS. No one can guarantee that this will not happen tomorrow. Of course, the more it has been used, etc., and examined, the more the confidence is built, but there is no, I would say, bulletproof solution. So, having said that about the confidence, apparently it's not us to talk about the confidence or not. This is expressed by the experts, by the cryptographers. We are not cryptographers, I'm not a cryptographer, so I will not say an opinion on this. NIST itself says that they are extremely confident about the selection, and this is why, as they mentioned before, they do not propose hybridization. However, as mentioned also before, they propose, in Europe, it's proposed to have hybridization so as if something goes wrong on the post-quantum solution, at least to have the pre-quantum solution to secure your information, at least until the quantum computers will be materialized. But regarding the crypto agility, crypto flexibility is mentioned in the question. The term usually used is crypto agility. It's an extremely good, valid point, and it is one of the major, I would say, requirements in all our developments from ISAC point of view that we are doing, that envisages to use asymmetric crypto for post-quantum. Crypto agility is an integral part of the solution, meaning that you need to be able, on demand, when you need, when you decide your crypto algorithms, even while flying. Of course, in order to be sure that this will not be broken, because the crypto agility has also to be secure, apparently it needs to be protected by some other algorithms, not by the one that you use for the other communications. And there are solutions about this. I will not enter into technical details, but there are solutions which are good for protecting the continuous, let's say, traffic with high throughput, a lot of data, etc., with many interactions, and maybe a bit, I would not say less secure, this is not a correct term, but it is the one that is under discussion here. And there are other solutions which are more trustworthy, to put it like this, meaning that, for instance, they are based on hash-based signatures. So there is much more confident for them. They have some other potential limitations that in the so-called stateful hash-based signature, you need to keep up the state. So they may not be ideal for protecting the everyday continuous traffic, but they are ideal for protecting this crypto agility, firmware updates, etc., which do not take every day or every month, but they take once every, whatever, 1 year or so. So yes, crypto agility is vital. Yes, when we plan a solution for post-quantum, crypto agility is an integral part of it, and yes, there are also solutions to protect this crypto agility.
Thank you. I'm going to use the last few minutes for a lightning round. You guys ready for this? So you have 40 seconds to answer this question. Okay, and I'm not going to pick the order, so just jump in when you think you have an answer. If we look back 5 years from now at a major space system compromise, something that should have been prevented, which decision do you think we'll regret most? Not moving fast enough on PQC, or over-investing in quantum solutions that couldn't be operationalized?
It's not about crypto, this one, I believe. We should not forget that, indeed, crypto is a vital pillar of our everyday life and for every system, but at the end of the day, security is not only about crypto. security is a combination of many things. And if we go back on the compromises, we will see that the compromises were not that much, certainly were not due to quantum threat to crypto, because quantum computers do not exist even today, so there was not any compromise because of this. Maybe there were compromises of misimplementations of traditional crypto, but at the end of the day, it's in total about cybersecurity. And what we should do faster and better in general is to have more cybersecurity in general in space. This is my view.
Yes, maybe to go in your sense, for sure that cryptography is one way to secure satellites system, but we also need to think that at system level. And for instance, we see this morning that jamming of satellites has been done through radio frequency systems, because you are in the area of the antennas, and you are able to connect any antennas to the satellite if you are far away from the ground station. But if you use, for instance, optical communications, the diameter of the link is only a few hundred meters on ground, so you can secure your link by using laser communication instead of RF communication. This is one way we are also exploring to globally think about the security of the systems. Cryptography for sure is necessary, but we also can increase the security of the system by different communications way, on the optical especially.
Johanna?
I think two things that are very regrettable. The first one is putting PQC against QKD. There are two different technologies with different capabilities and like the killer use cases. So these have to work together. If we had put them together, we have joined two communities, and I mean the physicists together with the cryptographers, together with the architects, and we already would have maybe certification of QKD. But we put this against, and we put this barrier, and this is delaying a lot us. The second thing is not thinking on the crypto obsolescence that we already have mentioned here, is that crypto obsolescence, this is not the last migration that we are going to have. Yes, we need the crypto agility together with all the process that we have to put in place in order to enable migrations. So we need to think of crypto obsolescence. We have to know that this is not the last time that we are going to migrate to another crypto solution, so we have to be prepared.
Anything you'd add, Sabrina?
Honestly, on the tech side, I think they got it covered, and completely agree with Johanna's point of view about pitting QKD and PQC against each other. And I think if we can do that, as you said, we'll see much faster deployment and collaboration. And then maybe on a less technical side, I think further collaboration between industry, research, and government needs to happen. Because right now I'm seeing a lot of it happen in isolation, great ideas coming up, but less kind of, as you mentioned, opportunity of let's just do this and make it happen. And I think that speed is what I think we might regret if we look back. But again, things are moving in the right direction, I hope. So yeah, I think hopefully now we're kind of picking that up. It's actually become so key to defense now and this concept of resiliency. So I think given the priority where the world and Europe is going, things will speed up a lot faster, and some of these challenges will be dealt with.
Thank you. We've learned a lot. Thank you so much to all of you for bringing your expertise. Space systems architecture will be more resilient in the future because of you, and secure, of course. So let's give a round of applause to our panel today. Thank you.